Okay, as promised, here are the three numbers. Let's find the standard deviation. Again, reminding you the formula is S is equal to the square root of the sum of the deviations x minus x bar squared divided by n minus 1. And so the first thing that I need to find is actually the average of these. X bar. What is x bar? X bar is equal to 1 plus 3 plus 14 divided by three numbers. So 1 plus 3 is 4, plus 14 is 18 divided by 3, which is the same thing as 6. Now, let's go find the standard deviation using the formula. What I need to do is S is equal to the square root of this long expression, where I'm going to add up x minus x bar. 1 minus 6 quantity squared plus 3 minus 6 quantity squared plus we have 14 minus 6 quantity squared, and all this divided by n minus 1, so 3 minus 1, which is 2. Simplifying some of these, we have the square root of this quantity 1 minus 5 is negative 5 squared plus negative 3 squared plus 8 squared divided by 2. So we have S is equal to the square root of 25 plus 9 plus 64 divided by 2, which gives us S is equal to the square root of 25 plus 9 plus 64 is equal to, should be 98. Divided by 2, and 98 divided by 2 is 49, and the square root of 49 is 7. So that's my standard deviation, and that is the average distance that my data points are away from the mean. Well, what's the mean? The mean is 6 in this case. Here are the numbers. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9. And so some of my numbers are right here. Here's 1, 3, and then over here I'll just put a dot for 14. Well, what's the average? The average is right here. It's 6. And so if you take a look at this, the standard deviation is telling us that on average, the data points are 7 units away from the mean. The mean is 6, and so 7 units this way and 7 units this way will contain most of the coordinate points, and we do. 7 points to the left contains 2 of the 3 points that we found. So that is how to calculate standard deviation by hand. Let's keep going. There is something called an empirical rule, and that is when you have a bell-shaped curve like this, which shows up in a whole bunch of different situations, when you calculate the standard deviation, one standard deviation away from the mean contains a certain amount of the population, namely 68% of the population, right? And this is, you need a little bit of calculus, of course, and I'll get to the calculus a little bit later in a future section. But the idea is that the area underneath the curve is representative of the probability, or the percent of people or subjects within one standard deviation. Within 2 standard deviation, it's 95%. Within 3 standard deviations, 99.7% of the data. So keep these numbers memorized: 68%, 95, and 99.7, respectively, for 1, 2, and 3 standard deviations away from the mean. Okay? Now, what if you don't have a bell-shaped curve? Well, there's Chebyshev's theorem for that. And this theorem applies to the distributions of any shape. And so you would hopefully expect that the percentages would actually be lower, because we're not guaranteed the symmetry in other different distributions, right? Bell-shaped curve has the symmetry. Whatever area underneath the curve is to the right, that's the same thing on the left. So, therefore, Chebyshev's theorem is not as telling or robust as the empirical rule, but that's okay. And the the proportion in the second bullet point here, or fraction of any set of data lying within k standard deviations of the mean is always, is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. So here's an example. Think about this. At least 3/4 or 75% of all the values lie within 2 standard deviations of the mean for any type of distribution with any shape. That's what Chebyshev's theorem says. And that's actually a pretty big conclusion to make, right? So let me draw you a picture. Here's the idea. If I had a bell-shaped curve, because of the symmetry, I would have a certain amount of area here and a certain amount of area here. Well, if I actually take one standard deviation away, x bar plus 1s, or I should say minus 1s, and then x bar plus 1 standard deviation like that, this would contain whatever this part is and whatever this part is, a total of 68% between, I'll use red here, between these two lines. Well, what if I don't have a bell-shaped curve? What if I have a different shaped curve, right? I'll just use a skewed one like this, for instance. The idea is that there will be a mean, an average. Maybe I'll put the average right here. It's going to be close to the highest frequency point. Remember that this is just the height of the curve is determining frequency. So I can say that this would be x bar, and then within one standard deviation of x bar, I would contain a certain amount. But do you notice that there isn't this symmetry? And that's why the percentage is actually lower. Within one standard deviation, we have roughly about 0%, or at least 0%. Well, that makes sense. Of course, we're going to have something within one standard deviation of the mean, right? Something greater than 0%. And then if within 2 standard deviations for not necessarily bell-shaped curves, we'll have 75% of the population. And we find this by using this calculation, 1 minus 1 over k squared. So if you think about it, 75%, where do we get that? Well, 2 standard deviations away would mean that we have 1 minus 1 over 2 squared, or 1 minus 1 over 2 squared is equal to 1 minus 1/4. 1 minus 1/4 is 3/4. That's how we got the 75%. So within 2 standard deviations of a distribution that's not necessarily bell-shaped curve, we have 75% of the data points. Okay? Hopefully that helps and builds your intuition about Chebyshev's theorem. Same thing applies with the 89% within 3 standard deviations. And here's a table that compares the two. Notice that in the Chebyshev's theorem, it says at least 0% of the data. The more that the data set represents a bell-shaped curve, the bigger the amount of data would be contained within 1 or 2 or 3 standard deviations. Notice we can guarantee at least something within 1 standard deviation, right? Then within 2 standard deviations, we guarantee 75%, and within 3 standard deviations, we carry about 89% of the data. At least that much. It could be more, and it is more if there was symmetry, right? Because the symmetry of the empirical rule of the bell-shaped curve, we have 99.7% of the data there. Okay. Unusual scores. Please note that this could be a test question. I can ask it different ways, but it says here for typical data sets, it is unusual for a score to differ from the mean by more than 2 standard deviations. Okay, so that's a boundary for unusual scores, 2 standard deviations or more. And so if we take a look at this, calculate standard deviation from the mean, we would just be counting by 3s. So 43, 46, 49 above, and then subtracting 3, going down from 40 to 37 to 34 and so forth. That gives you 1, 2, and 3 standard deviations from the mean. And then the boundaries for the maximum and minimal usual values would be within 2 standard deviations. So 40 plus 3 twice would give you 46. That's the upper boundary. If you subtract 3 twice from 40, you get 37 and then 34. 34 and 46 would be the boundaries for the maximum, minimum, usual values, and therefore everything outside of that interval would be considered unusual. Okay, so you can use this as an exercise for practice, applying the empirical rule and applying Chebyshev's theorem. If we do have that the standard deviation is 0.07, and then the mean, the average, is 4, it says a batch of volts has a mean of 4 inches and a standard deviation of 0.007 inches. What can you conclude about the percentage of volts between the various intervals? Well, take 4 and add 0.007. That's one standard deviation. If you had a bell-shaped curve, you know that there's 68% of the volts will be within one standard deviation, so 4.007 inches long, or subtract 0.007 and you get the lower boundary of your one standard deviation. If you take one more standard deviation, then you'd be in this interval right here, 3.986, the lower boundary, and a 4.014 would be the upper boundary for this 2 standard deviations, right? And if it was not bell-shaped, then Chebyshev's theorem says that within 2 standard deviations, you have at least 75% of your data points. Okay, let's take a look at a more concrete example. Anya is considering investing in ProSoft, a software company that specializes in smartphone applications. She intends to compute the standard deviation of its recent prices to measure how steady its stock price has been recently. The following are the closing prices for the stock for the past 20 trading sessions. And we have a list of 2 rows of numbers. What is the standard deviation for this data set? Go ahead and you can pause the video and actually try this either with the calculator or by hand, and you would be able to get a standard deviation. And if the standard deviation is relatively small, which it's going to end up looking at the numbers, it looks like intuitively the standard deviation is going to be small. That means most of the data points are really close to the average. They're not that spread out, right? So that's what standard deviation is a measure of. One really quick thing about the connection between range and standard deviation. The range is 4 times, or again, this is really rough. The range is approximately 4 times the standard deviation. So you can actually approximate one having the other. Approximate the standard deviation using the range rule of thumb. Well, if you think about this, I just need to find the range, right? So if you take a look at the largest value, which is 16, and the smallest value is 9, subtract one from the other, and you get 7 for the range. And since the range is 4 times standard deviation, so if I want the standard deviation of this data set, I just need to take 7, 16 minus 9, which is 7, and then divided by 4. 7 divided by 4 would be my standard deviation. Again, that's not exactly the standard deviation. That's a really rough estimate, and there is that connection there between range and standard deviation. Okay. I'm going to make actually a separate video for the coefficient of variation, which starts with this slide. So let's go on, try some more homework exercises in section 3.3, and let's take care of coefficient of variation in a separate video.